This problem, we have a second order reaction. What we have is a two-phase batch reactor where the reactants and the products are in an organic phase, and the second phase is water, and the reactor is mostly water. And the problem says that the water is completely immiscible with the organic phase, and the water phase is continuous. So that means we have this phase of water and we have droplets of the organic phase. So this is water, and these are the organic phase. 1 mole going to 1 mole. We have a stir that's keeping these droplets dispersed. And the question is, how's the total rate of formation of this product B change with time? And so if we were to write a mass balance for this system, the change in the number of moles of A with time, because it's a second order reaction, it's squared times volume. The organic A going to B, liquid phase. Reasonable approximation is that the volume does not change significantly, so that we could factor the volume outside the derivative, and then we could say that means the volume cancels, and then we can separate variables and integrate from 0 to t from our initial concentration to our concentration at a later time. And this is just 1 over Ca with a minus sign between our initial and final values, and this is minus Kt. So I've solved concentration in terms of time, the rate constant, our initial concentration. Problem asks for the total rate of formation of B. So this, since it's A goes to B, is the rate constant, Ca squared, times the volume of the organic. And we could, of course, write this as 0.20, the total reactor volume. 20% is organic and 80% is water. And so our overall total rate of B formation then is given by this equation where V is the total reactor volume. And the concentrations, Ca0, and of course the concentration of A in this calculation is the concentration in the organic phase. In this problem, we have an isothermal packed bed reactor, and we're carrying out a first order reaction of 2A goes to B. Important that we mention this is the gas phase reaction. And at the outlet of the reactor, we've converted 50% of A. We've also dropped the pressure because it's a packed bed from 10 bar to 5 bar. And the question is, what's the ratio of the outlet velocity to the inlet velocity? It's an isothermal system, so pressure drop and mole change are both going to affect these. And same question is, what's the ratio of the outlet volumetric flow rate to the inlet volumetric flow rate? So we write the volumetric flow rate coming in terms of the total molar flow rate, RT over P. Don't know these values in numerator. Denominator is 10 bar. Now we can write the same equation where the number of moles has changed because 2A goes to B, RT is the same, and the pressure is 5. And we can calculate F total, leaving it's FA plus FB. Well, half of the A is reacted, so this is half of FA0. When a half a mole of A reacts, you make a quarter mole of B, so this is 0.25 FA0. So 0.75 FA0. Now, F total is FA0 because we're assuming only A enters this reactor. And so this means V0 is FA0 RT over 10, and V final is 0.75 FA0 RT over 5, which is 1.5 FA0 RT over 10. So V is equal to 1.5 times V0. This is volumetric flow rate. So this means velocity is 1.5 times initial velocity.